All right, so welcome to a section of notes on the Pythagorean Theorem. This, for Math 8, is 7.3. So it's 7.3, the Pythagorean Theorem, and it's all based off being able to find square roots. Not necessarily complicated square roots, but square roots in general. One thing that might be helpful while you're doing this is to just understand where this list is coming from. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5, 25. And I'm just writing down a bunch of numbers that are called perfect squares. They're called perfect squares because if you take a number and square it, it comes out to these numbers perfectly. So these are all of your perfect squares, and having these in front of you is always helpful when working with these. So what we want to do is we want to talk about the square root of, let's say, 1.44. And if we're just trying to find the square root of 1.44, we look at a number on this list and we say 144 is that number. So what number multiplied by itself got us 144? It was 12, right? So we know that it was 12. So the question becomes, there's a decimal here, so do we realize that that's going to be 1.2 or 0.12 or 1 or just 12? So think about that, yes. 0.12. Okay, so if we change it to 0.12, now we have to test our answer. So if we make it 0.12 times 0.12, does that come out to 1.44? Because 0.12 is pretty small. So I think it's going to be a really small number. So I've got 4, I've got 2, I put my 0 in there, I've got 12, I've got 144 for sure, but I have 4 decimal places. So I would be way the heck over here, right? So it's actually not going to be 1.2 in this case. It's not going to be 0.12, it's going to be 1.2. Now how do we know it's 1.2? Well, let's try the same thing again. 1.2, 1.2, multiply it out. You'll notice that when you're multiplying it, you now have 2 decimal places, right? Because each number is off by 1. So we got 4, we got 2, we got 0, we got 1, 2, we got 144, but we got to move it 2 places. So we have 1.44. So the answer to 1 is 1.2. So the Pythagorean theorem is going to be applying these types of problems. So look at these problems, make sure they feel comfortable, but especially make sure you're able to do a straight up problem like the square root of, let's say, the square root of 9 is 3. Or the square root of 12 is about, right, well, it's somewhere between 9 and 16. So it might be, let's say, let's see. We know 9 is on the list. We know 16 is on the list. We know 12 is a little closer to 9. So I would say it's about 3.4. It's a little closer to 3 because 3 squared is 9 than in 4. Because 12 is not quite halfway in between, right? So these are the types of things we need to know to be able to do the Pythagorean theorem. So the cool thing is the Pythagorean theorem is really going to help us with triangles, geometry, stuff like that. So this example is where we want to start. Find the missing side length of the triangle. So we see on number 1 that that first side is 6, the second side is 8, and the third side is C. So the Pythagorean theorem states the following. Let me show you before we go on too far. I think I'll write it out myself. When you have a right triangle, like, let's say, for example, this, it has to be a right triangle. You're always going to have this little thing pointing to your hypotenuse. So this is your hypotenuse. Okay, and I like to think of it as the hippo, right? The biggest side on the triangle. So when you look at the right triangle, the largest side is the hypotenuse. So the Pythagorean theorem says the following. The Pythagorean theorem says, and it's an important theorem. I'm not gonna lie to you. Most of your parents, if you went home and asked them, they would probably at least remember hearing about the Pythagorean theorem. The Pythagorean theorem says in a right triangle. So that means it's a triangle that has a right angle. So it has to have a right angle. So when I say right triangle, it has to be like that, right? In a right triangle, where C is the hypotenuse. And we remember hypotenuse kind of sounds like hippo, right? A squared plus B squared is equal to C squared. So this is always going to be the case. That's the actual theorem in the green box. A squared plus B squared equals C squared. So hippo is a big animal. The hypotenuse reminds you of hippo. It's the biggest side. And the right angle symbol, you see the 90-degree angle symbol over here. That's like a little square. It's always going to kind of point to you where the hypotenuse is. So you can kind of see that and figure out that that's the hypotenuse. So what's going to happen is whatever number is here, let's say, for example, you had 3 here and you had 4 here, okay? What you're going to do is, it doesn't matter which one you think of as A and B, as long as you have the hypotenuse by itself. So I took C squared. Now, I don't care if you make 3 your A and you do 3 squared plus 4 squared, or you make 4 your A and you do 4 squared plus 3 squared. As long as your hypotenuse is alone, the biggest side, by itself. So what I'll do is I'll usually pick the smallest one, 3 squared, plus 4 squared. Now, why am I squaring them? Because that's what the theorem says. The theorem says that it will always work out that way, okay? So 3 squared is 9, 4 squared is 16. So I have 9 plus 16 is equal to C squared. Well, we know that 9 plus 16 is equal to 25. So we now have 25 is equal to C squared. The question becomes, if C is now squared and we want to know what actually C was, what squared is 25? Yes. 5 squared is 25. So C must be 5. C equals 5 for that reason. Now here's another way of thinking of it, okay? Now some people might go on this little island here. You have 25 equals C squared, and you say, how do I get rid of a squared? What is the opposite of squaring something? Well, 2 squared is 4, and the square root of 4 is 2, right? 5 squared is 25, and the square root of 25 is 5. 8 squared is 64, and the square root of 64 is 8. So the opposite of squaring something is square rooting. So you can do something that's very important. Instead of adding to both sides or dividing by both sides, you square root both sides. Square root both sides, square root both sides. Okay? We're only going to talk about positive square roots in this situation. So right now we're just going to say C is equal to the square root of 25, right? Which is 5. So you got it both ways, right? Now, the thing is, you could say, wait a minute, though, wouldn't negative 5 had worked as well? But do you really want negative 5 for a side length? No. So we're going to just look at the positive aspect of this. And that tells us that this triangle is exactly 5 on the hypotenuse. Okay, so that's the basics of the Pythagorean theorem. All right, so now what we're going to do is we're going to talk about a slightly different example. Slightly different. Okay, so here's what I'm going to do. I'm going to do example 2, and I'm going to have a triangle that looks like this. Okay, and on this triangle I have a couple of things. I have this, which is missing, okay? I have this is 12 and this is 13. So this is my second example. We don't want to use the Pythagorean theorem, so the first thing you're going to want to do is identify the hypotenuse or the hippo. So can we identify the hypotenuse or the hippo? It's 13. The biggest of the sides is 13 visually, so this is what we want to do. We want to just kind of isolate that and realize that that is the hypotenuse. And again, I just use hippo because I am lazy. So the theorem says that the 13 has to go with the other numbers or by itself. By itself. This is the special side. So 13 must be squared all by itself over here. Now the other two things need to be squared and added together, but it doesn't matter the order. So I don't know which you prefer to put first. Do you want to put x and square that plus 12 and square that? Or 12 and square that plus x and square that? It doesn't really matter, right? So I'm going to put x squared plus 12 squared, if that's okay. This is the theorem. This is all based off of the theorem. Now we just straight up have to do all of the math out. So we can't really square x, but we can square 12. So I'm going to take 12 and square it. So I'm going to put a little dividing line here so we know where we're working. 12 squared is 144. 13 squared is 169. You can just do 12 times 12 and 13 times 13 if you need. Are there questions about that? Is that all looking okay? Yes? What is not able to be dealt with is the x squared. So that just comes down and has a plus there. So everything's just come down to one more step. Now the question becomes this. What do we do here to get what x is? It's a little bit weird. Yes? Yes, get x alone just like you normally would, even though it's squared. So we're going to subtract 144 on both sides, which is kind of what your common sense tells you to do. You kind of know that's what you're supposed to do. 169 minus 144 is actually, what is it? 25? Oh, and that's brilliant because 25 is what squared? 5 squared. Now, if we didn't know it, we would just square root both sides. So the way we would get the answer is we'd square root both sides. Whatever you do to the left, you do to the right. Square rooting a square cancels out. So what I'm going to do is I'm going to cancel this with this and get just x. Square root of 25 is 5. That's my answer. Okay? That's my answer. So the actual other side of this triangle is 5 units long. Pretty interesting. What's kind of cool is that you can kind of see this working out in some ways with like patterns and visuals. So I'm going to show you one more thing and then we'll wrap it up. So you remember that the first example that we had done, sorry if that was too fast. You can always pause the video if you need to. So take a look at that, okay? So what's kind of cool is that we can always use visuals to understand what's going on here. So if I took this, for example, this triangle right here, which was 3, right? And I went and divided this into 3, and I squared 3, I would have this. Do you see that? So that side is 3. Do you agree it's 3 blocks long? Okay. Now my blocks might not be perfectly in size, but I'm going to do my best, okay? So now my next one is going to look like this. Okay. I'm just making squares because we're squaring things, right? And well, it's not perfectly drawn, but what I'm trying to do is show you that if we have the 3 and the 4, right? So what I've done is I've basically made 2 different boxes here, right? And they're not supposed to be different sizes. All those boxes are supposed to be the same size. But it's an imperfect drawing. So what I'm doing is I'm drawing squares. I'm looking at this thing and I'm drawing squares of it. So I'm looking at these lines and I'm trying to just draw a square. So you see that I'm running out of space here. I'll try to give myself a little bit more. Go all the way to the bottom. Here we go. And there we are. Okay? So if this is 3 and 4, we had that example that was 5. Now this might be a little confusing, but try to at least work with me for a few minutes because you'll see something cool happen in a second. Okay? So 1, 2, 3, 4, 5. So let's make the squares off of that. I'm just making squares, people. I'm just making squares. Okay. Ooh, that's ugly. The artistry is kind of tricky on this, huh? Okay, you might be wondering what the heck is he doing? Well, if we're squaring thing, I'm just making squares. So now I've made a little square, a medium square, and a big square. Do you see the small waffle, the medium waffle, and the large waffle? Yes? Okay, here's all I'm doing, okay? We know that the answer for previously, I'm just going to flip back for a second, was 3, 4, and 5. Do you see that the C came out to be 5? So I've drawn this triangle again over here, and what I'm doing is I'm showing you something, okay? What I think is kind of cool is I'm just going to do the following. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Would you agree there are 25 red dots between those two? If you took this one and you added this one, right? 25 red dots. Now the question is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we could also say there are 25 blue dots, right? And this is what the Pythagorean theorem is saying. If you take the sides, right, if you take the sides and you look at them, they're going to be the same when you square them. So this is just me visually showing you proof that a squared plus b squared equals c squared. Because if this is a and I square it, I'm going to get 9. If this is b and I make a square out of it, I'm going to get a square with 16 spots. And if I take c and square it, I'm going to have a 5 by 5 in this case, which would be a square with 25 boxes. The number of boxes that the hypotenuse square makes will always be the same to the number of boxes that the a and the b make. So we have the same number of, it's the same amount of waffles. Would you prefer to have the waffle C, or would you prefer to have waffle A and B? Doesn't matter, because it's the same amount of food, right? Waffle A and B, a little waffle and a medium waffle, is the same as the big waffle in this example. So that's just a quick visual of it, not really a lot there. So what you're going to need to do is practice a little bit. So what I want you to do is a couple of problems here. A now you try. Whoops. A now you try. So your now you try for this is the following. I want you to do this example right here, number 1, and this example right here, number 2. The first one is this one right here. Okay. And it's going to be the following. I think it's going to be, let's see. I don't know. Let's say it's 6 and 8, and this is unknown. Okay, this is a right angle. And then let's also do this one right here, which is the following. It looks like this. And let's say we have here, I don't know. Let's say we have 13 and 5 here, and then just find this one. We'll call that y. So this is your now you try. So pause the videos, give these two a try. Make sure you show the work, even if you see something. Show the work to get there. Pause the video and give that a shot, and I'm going to wrap it up here. Peace.